As we noticed in the previous video, there's not just one right guess for whose derivative am I in the anti-differentiation game. And that leads us to the following theorem. If capital F is an antiderivative of function lowercase f on an interval from a to b, then every other antiderivative on that same interval is of the form capital F plus c for some constant c. A short way of saying this, or a more intuitive way of saying this, is just that every antiderivative of a function differs from each other by a constant. We may all come up with different antiderivatives for a function, but we'll differ only by a constant amount. All right, and the notation that we'll use is mysteriously similar to the notation from the previous section for definite integrals. We see this very tall-looking S, which in fact does ultimately stand for sum, although it's not clear why in this section it does, because in the last section when we used this symbol, we were adding up signed area. In this section, we're doing a totally different procedure. We're anti-differentiating. We're undoing the process of differentiating. And it should not be at all clear why we use the same symbol. But in this notation, this is the integral symbol. This function that we're finding the antiderivative of is called the integrand. Dx is the differential. It kind of tells us what variable we're integrating with respect to, or we're finding the antiderivative with respect to. This whole, and it's part of these two pieces go together, and then the integrand sits in the middle of them. So these two pieces form the notation that says, hey, we're finding an antiderivative. This whole thing is the antiderivative. Or the indefinite integral. And the capital C is referred to as the constant of integration. And the process of finding an antiderivative is called integration, similar to the process of differentiation, the process of finding a derivative is called differentiation. Now, when we write all of this notation together, that means, so this is the indefinite integral of f, and what that means is, when we take the derivative of this function, the antiderivative, we're going to get the integrand. Some integral rules. Let's cover that one. Like we were looking at a moment ago, in the examples, to undo the process of differentiation for a polynomial type expression, when you're differentiating, you bring the power down front and then you have the base to the one less power. To undo that process, we augment the power by 1, and then to offset that constant out front, we divide by n plus 1, and then we add that general constant of integration. Again, you don't just have to guess and say, well, I think that's right. I think that's what it should be. Differentiate this piece. Differentiate any constant, you get a 0. So this is inconsequential. Differentiating this piece, you bring the power down front, n plus 1, divided by this constant n plus 1 in the denominator, and then x to the 1 less power. So those n plus 1's cancel, and you just end up getting x to the n. So whose derivative is that? This guy. If you take the derivative of this function right here, actually this whole thing, take the derivative of this function, you get the integrand. Another derivative rule that we practiced in the examples was who is the antiderivative of 1 over x? Well, the indefinite integral of 1 over x dx, which you also may see written this way with that differential written in the numerator, is the natural log of the absolute value of x plus c. To check it, take the derivative of the natural log of the absolute value of x, or natural log of x, and you get 1 over x. these absolute value bars are here just because we don't know the x values for which we're considering this antiderivative. If they're positive x values, those natural log, those absolute value bars are not needed. If they're negative x values, you do need the absolute value bars there because, as you recall, natural log accepts as inputs only positive real numbers. There's a couple of others having to do with the trig functions. So when you integrate sine of x, you get negative cosine of x plus c. That might seem a little backward because it's sort of the reverse of the differentiation rule, but this is a reversing process. Take the derivative. This is your capital F function. This is your little f function. So to check this process, take the derivative of the capital F function. The derivative of cosine is negative sine, which will be hit with this negative sign that's already there to give us just plain old sine of x. Okay, so if you're ever in doubt about an antiderivative, check it by differentiating. Similarly here, this is our little f, that's the integrand. This is our big F, that's the indefinite integral. If you differentiate sine of x, you should get the integrand, cosine of x. Okay, we won't go through all the rules on the video because you guys have a very expensive calculus book that has all this information in it. See the other rules that are sprinkled throughout the section. There are some rules having to do with integrating exponential functions and constant corrections on them. There's also some basic trig integrals where you look and see for functions that are obviously someone's derivative. Like if you encounter secant squared of x, well, whose derivative is that? It's tangents. So you'll see those rules at the top of page 284. And also very concisely summarized for you in the summary on page 5.3 of section, summary on page 286, section 5.3.